All right, so last time we finished the second module. The second module finished the uh, introductory types of slides, and now we're moving to slides that cover uh, probability and models. So in this set of slides, we're going to talk about probability. It'll be a review. Hopefully you're familiar with that. And if you feel uncomfortable with that material, you should probably be in touch with myself, the TA, and consider whether you can catch up. After that, we'll discuss machine learning terminology. And finally, we'll be discussing models. That'll be this set of slides. You're expected to have an undergraduate probability background as a prerequisite, and we're going to provide a fast-paced probability review. And probability naturally leads to models for data. And the simple models, they're tractable. That could be computationally tractable, mathematically tractable. Basically, they're simple, but they may not explain real-world data well because real-world data is often very complicated. On the other hand, complicated models, they may capture the data better, but they're intractable computationally, mathematically. Basically, they're difficult to work with. So there's inevitably a trade-off between the two, and we're going to formalize this trade-off, allowing you to have some understanding of how to choose reasonably complex models. So again, we're in modules number 3 and 4. We'll be having a probability review. So we're beginning with a probability space that contains 3 concepts: omega, F, and P. And these 3 components are as follows. First of all, omega is the sample space. Omega is the set of all possible outcomes of a random experiment. Example number 1, you have a coin flip. Your possible outcomes could be heads and tails, H and T. Omega will be the set that includes 2 elements, H and T. You can also think about a second example. The second example could be you're tossing a die. And in this case, the possible outcomes will be 1 through 6. And because of that, omega will include the numbers 1, 2, 3, 4, 5, and 6. So that's the sample space omega. The sigma field denoted by F is comprised of events, and there are some requirements on those events. But first of all, what is an event? Events are subsets of the sample space, omega. So first of all, the empty set must be in the sigma field F of events. Secondly, omega itself must be in the set F. Now there are 2 more requirements. If A and B are events in F, then their complements must be in F. So A complement and B complement must be in F. And secondly, if A and B are both events in F, then their intersection must be in F. Now, if their intersection is in F and their complements in F, it can be shown that their union also needs to be in the set F. So we have a sample space omega, a sigma field F, which has closure to intersection, closure to union, closure to the complement. And finally, we have the third component of a probability space is P. Omega, F, and P, the probability space, which is assigned to events, and details on the next page. An example of a sigma field F, recall that I started in example 1 with a coin flip, 2 different outcomes, H and T, heads and tails. I could now consider a sigma field F that contains all the subsets of omega: the empty subset, the subset that includes only heads, the subset that includes only tails, and omega itself, which includes both H and T. So what about the probability space B? I gave you some requirements for the sigma field F. I said that there needs to be closure to complement, intersection, and union. Probability space also needs to satisfy some conditions. So first of all, it's a function that assigns a number in the range from 0 to 1, and this is a closed range, and it's a closed range because I'd like you to see these squared brackets. And in contrast, an open range would be denoted by 0 to 1 with parentheses. And the parenthesis near 0 means that it's open at 0. This latter set does not include the number 0, whereas with square brackets, it does include that number. So first of all, the probability space P assigns numbers in that range. And for every probability space P, it's a function, but it's not any function. It must satisfy, first of all, the probability is always greater than or equal to 0, no matter what event. Secondly, the probability of omega, the set of all possible outcomes, is 1. Now that makes sense. If we think of a Venn diagram, omega would be the set of everything. And let's say that this will be T, and the rest will be F. And omega will include both T and F. And the empty set means that neither T nor F happened. And we have the area of T may correspond to a probability, and the area of, well, the rest of the time, F may correspond to another probability. And the sum of the two probabilities should add up to 1. That's our intuition. So first of all, non-negative probability. Secondly, the probability of omega is 1. And finally, if we have two disjoint events, A and B, and disjoint means that their intersection is the empty set, then the probability of the union is the sum of the probabilities. For example, let's modify the example. The probability of the empty set is going to be 0. Let's say that the probability of heads is 0.4. Now, the probability of tails, the tails set is disjoint from the head set, and the probability of their union, the probability of H and T, is equal to the probability of omega, because H and T are the only two possible outcomes, which is equal to 1. Now recall, again, H and T are disjoint. Therefore, the probability of H, and recall, the event is not just H. The event is the subset that includes the outcome H. H is an outcome, and the event is a subset of omega. Probability of H plus the probability of T, because they're disjoint, I have an arrow from the word disjoint to the equal sign. It's equal to the probability of the union. The probability of the union, we agreed that it's equal to 1. We agreed because that's the probability of omega. And the probability of H is 0.4, and therefore the probability of tails should be, in this modified example, 0.6. Now, of course, in all the probability textbooks, they tell you that heads and tails have equal probability, but I just wanted to show you the example can be made a bit more complicated. All right, so let's move on. Here's a question. I suggest I'll present the question, then I'll suggest that you pause the recording, and after that I'll work through a possible solution. So consider tossing a fair die. Again, it takes sides 1 through 6, and propose a probability space with components omega, F, and P. So please pause for a few seconds, and then I'll start solving. All right, so I'm back, and I'll sort of type through this. So recall that we said earlier that omega, it makes sense that it would be the 6 outcomes would be the 6 possible values 1 through 6. And then F is a field of events, and events are subsets of omega, right? So you could say to yourself, oh, there's a single solution here, but actually they're different solutions. And let me illustrate 2 solutions. F1 would be a very, very simple field. It would only contain two different events, the empty event and omega itself. P1, probability space number 1, corresponds to F1 field number 1, and P1 is a function from 0 to 1 that assigns probabilities to the two events in F1. So it makes sense that the probability of the empty set is 0, and the probability of omega is always 1, and that's it. So if somebody asks you, what's the probability of the fair die landing on the number 1, you'll say, well, if you're following your intuition and you're not thinking very carefully through the definitions, you'll say 1/6. But based on our definitions, we don't know, because the outcome of landing on side number 1 has not really been defined. So this is a silly set of events, F1. So F2 will be a realistic set. So it'll include the empty set. It'll include 1. It'll include 2. It'll include 3. It'll include 4. And so on. And it'll also include omega. Now, what is the cardinality of F2? And cardinality means the number of elements in F2. So if you think about it, there are 6 elements in omega. And each element could be in an event or not. Therefore, there are 2 to the power of 6, which is 64 events in F2. What about probability 2? For the second field F, we want a second probability function. It's natural that P2 assigns to event E the number of elements, the cardinality of the event E divided by 6. For example, e.g., the probability of what I was asking earlier, that we landed on the side 1, is the cardinality of the set that only allows us to land on 1 divided by 6, which is 1/6. Similarly, you could calculate the probability of landing on an even number, an odd number, etc. And that leads to a third example, F3. Let's build a field that answers the following question. Want to answer, did we land on an odd side? So F3 will, as always, the empty set, omega. It'll have the odds, 1, 3, 5. And recall, if it has 1, 3, 5, it must have the complement, 2, 4, 6. Now, you can show that F3 is valid, meaning that there's closure to complement, intersection, and union. And I'm not going to show that, and let me suggest that you may want to work out the details and send to me in the TA. Okay? For those of you who want to kind of work through this more carefully. So F3 is a valid sigma field. And now what about P3? So P3 assigns probabilities to the 4 different events in F3. As always, the probability of the empty set is 0. The probability of omega is 1. And the probability of 1, 3, 5, well, we have 3 out of the 6 possible outcomes, and we're assuming that it's a fair die. That was what's given to us at the beginning. So let's just say that the probability of 1, 3, 5, the odds, are 1/2, And similarly, the probability of 2, 4, 6 is also 1/2 because there are 3 different outcomes. So if we ask you such a question on the test or the homework, a reasonable approach would be perhaps give us one field and the corresponding probability space, or another possibility would be give us 2 different fields. And it might be, just to make it a bit more interesting, it might be just slightly different. Instead of 6 different coin tosses, it could be that you are, I don't know, picking, you have 10 cards and you're picking one out of the 10 cards, and whatever the question would be. So these are the types of questions that may be involved in probability. All right, so let's move on, and hopefully that explanation is clear. The next concept is going to be joint and conditional probability. The joint probability is a probability for multiple events occurring jointly, and the word jointly means together. As an example, imagine that we have two different events. A will be the event that corresponds to temperature being above 50 degrees. And as you know, in August, when I'm recording this, the probability of a temperature above 50 degrees is very high. And B corresponds to the wind being more than 10 miles per hour. Now, I made up these probabilities. The probability of A, moderately high temperature, and the probability of a moderately high wind are both 0.5, but the probability of the joint event is only 0.2. So that leads to the next definition, of conditional probability. Given that, or conditioned on, that the event A happened, what's the probability of B? So for example, the probability of B conditioned on A is the joint probability, but let's envision this in a Venn diagram. So we have the space omega, and we're conditioning on A. So let's say that this is A, and let's say that this is B, and the probability of B conditioned on A is that we are conditioned on the blue shaded A. What is the probability that we also have B? What's the blue red shaded part as a fraction of the blue part? And of course, area in the Venn diagram does not need to have a one-to-one correspondence to probability. I'm just trying to provide intuition here. All right, so we're taking the joint probability, which corresponds to the doubly shaded part, which is 0.2, and we're dividing by the probability of A. So the doubly shaded divided by the shaded, that's the probability of the doubly shaded, or B conditioned on A, and the probability of A is 0.5, and 0.2 divided by 0.5 gives us 0.4. Next, we say that, so we have joint probability, 2 events happening, or multiple events, could be more than 2 happening together. Conditional probability, once we have joint events, we can calculate the probability of one event conditioned on another. And 2 events are independent if and only if the probability of A conditioned on B, any value of B, is equal to the probability of A, and the probability of B conditioned on event A is the probability of the event B. So these guys are not independent, and they're not independent because the probability of B is 0.5, and the probability of B of 0.5 is different from the probability of B conditioned on A, which is 0.4. Bayes' rule. So recall that the probability of the joint event, A and B, is the probability of A multiplied by the probability of B conditioned on A. It can also be expressed as the probability of B multiplied by the probability of A conditioned that we're in B. And this relationship leads to the probability of A conditioned on B, and this is similar to what we did in the previous slide using the Venn diagram. It's equal to the joint probability for A and B divided by the probability that we're conditioning on B. Now, on the other hand, with this Venn diagram type of interpretation, the probability of B is equal to the probability of A and B plus the probability of, and when I'm saying A and B, I mean A jointly with B, plus the probability of A complement occurring jointly with B. Because we have this Venn diagram, this would be A, this would be B, and let's say that A complement will be the shaded area outside of A. So what I'm saying here is that the probability of B contains two disjoint sets. One is this blue shaded stuff. So the probability of B jointly with A complement. And we also have the probability here, the probability of B jointly with A. Now the joint probability of A and B is the probability of A multiplied by the probability of B conditioned on A from before. And the probability of A complement occurring jointly with B is the probability of A complement multiplied by the probability of B conditioned on A complement. This leads to the following Bayes rule. The probability of A conditioned on B is equal to the probability of A joint with B divided by the probability of B. The probability of A happening jointly with B is the probability of A multiplied by the probability of B conditioned on A. And the probability of B that we're dividing in the numerator is the probability of what we had in the numerator. Probability of A multiplied by probability of B conditioned on A, plus this second term, probability of A complement multiplied by the probability of B conditioned on A complement. Now, Bayes' rule is used very frequently in statistical areas, and it's named after an 18th century statistician who put together this result. Finally, last slide of this module. So consider two events. A is the event that the height of a student is larger than 7 feet, and B is the event that a student has purple eyes. And suppose that the probability of A is 1/2. So let me start jotting that down. A is 1/2. The probability of B, purple eyes, is 0.3, and the joint event is 0.05. Now we're asking, what's the probability of the height being greater than 7 feet conditioned on purple eyes? So again, I'd like you to pause for a few seconds and then I'll continue. All right, so I'm now continuing. The probability of height greater than 7 conditioned on purple. Let's convert this to A and B notation, else it'll just be very difficult to write. So this is so height greater than 7 is A, and we're conditioning on purple eyes. Student having purple eyes is B. By the way, I said before that oftentimes I just make up examples. So obviously the example of purple eyes is completely contrived, and we have very few students. I've never actually taught a single student with height greater than 7 feet, so that's obviously very rare. So these are kind of made up examples, okay? So we want to calculate the probability of A conditioned on B. And the probability of A conditioned on B using Bayes' rule is the probability of the joint of A and B divided by the probability of B. Now the probability of the joint A and B was given to us as 0.05, and the probability of B was given to us as 0.3, and 0.05 divided by 0.3 is 1/6. So that's it for this example. That's it for the third module.